Imagine for a fleeting moment a boundary in the cosmos, so profound, so utterly inescapable, that to merely cross it is to embark upon a journey from which no return is possible, a voyage not just through space, but through time itself towards an ultimate, undeniable end. We are about to embark upon a contemplative expedition into the very heart of such realms, to explore the enigmatic nature of black holes. Those celestial titans that have, for generations, captivated the minds of scientists, philosophers, and dreamers alike. These are not merely distant astronomical curiosities. No, I believe these astonishing entities could very well be the ultimate key, the pivotal discovery that unlocks a complete quantum theory of gravity. Such a theory, my friends, is no mere incremental step in our scientific progress. It represents nothing less than a deeper, a more fundamental, a truly holistic understanding of reality itself. It is the pursuit of a grand unified framework that explains how space and time, those seemingly absolute and unchanging arenas of our brief lives, truly function at their most elemental, most intimate level. It is a quest to unveil the universe's most guarded secrets, to peer behind the curtain of observable phenomena and grasp the underlying mechanisms that govern all things, from the smallest ephemeral subatomic particles to the largest sprawling cosmic structures. And yes, my intuition, honed by decades of scientific inquiry and theoretical advancements, resonates with a growing sense of conviction in this profound possibility. So, what exactly are these profound cosmic entities, these black holes, truly concealing within their shrouded depths? What intricate secrets do they meticulously guard, hidden beyond that point of no return? These particular objects, which have journeyed from the ethereal realm of purely mathematical conjecture to the firmly established bedrock of astronomical observation over the past 4 or 5 decades, have, in their theoretical formulations, been subjects of intense fascination for much longer, indeed, for the better part of a century. They are, without any doubt, profoundly odd things, challenging our conventional understanding of physics, pushing the very boundaries of what we once considered possible within the vast, awe-inspiring expanse of the cosmos. The most straightforward, yet deceptively profound, way to describe a black hole is to conceptualize it as a region of space, a cosmic abyss, from which nothing, not even the swiftest entity in the universe, light itself, that ultimate cosmic messenger possesses the capacity to escape. This singular defining characteristic is what imparts to them their iconic, evocative name and infuses them with their deepest, most unsettling mysteries. It is the very essence of their bewildering nature, a boundary that marks an irrevocable transition from the observable to the unobservable, from our universe to a realm forever veiled. How can something be both intensely present and utterly invisible? This is one of the first profound questions they pose to us. The initial predictions regarding the existence of such extreme objects, the very first whispers of their possibility, can be traced back to the foundational work of Albert Einstein's general theory of relativity, a revolutionary paradigm unveiled at the dawn of the 20th century. Einstein's theory, with its elegant and sweeping equations, hinted at the inevitability of such gravitational behemoths. It was a conceptual leap of unimaginable audacity, suggesting that gravity was not merely a force, an invisible hand reaching across the cosmos, but rather an intrinsic manifestation of the curvature, the warping, of space and time themselves. However, despite these early, rigorous theoretical insights, it is crucial to appreciate that for a considerable period, spanning much of the mid-20th century, indeed, stretching well into the 1960s and arguably even into the 1980s, a significant portion of the global scientific community, including many of the era's most brilliant minds, harbored profound skepticism regarding their actual physical manifestation in nature. The primary driver of this widespread scientific hesitation was not a perceived flaw in the mathematical elegance or consistency of the relativistic predictions, but rather the sheer immensity of the intellectual and conceptual challenges that these predicted objects posed. Their properties seemed so utterly extreme, so wildly counterintuitive to the prevailing understanding of a cosmos that many expected to be, in some fundamental sense, orderly, comprehensible, and ultimately benign in its extremes. It was almost as if the universe, in its elegant design, would somehow find a graceful way to circumvent the formation of such truly bewildering and perplexing entities. I recall an anecdote, a sentiment attributed to the esteemed physicist Steven Weinberg, a towering figure in modern physics and a Nobel laureate whose groundbreaking contributions profoundly shaped our understanding of particle physics and fundamental forces. He once conveyed, with a certain intellectual humility, that he, in a deep sense, hoped that these cosmic behemoths would ultimately not exist. His reasoning was not a dismissal born of ignorance, but rather a frank acknowledgement of the immense conceptual complexities they introduced, a recognition that their undeniable existence would necessitate a radical reevaluation of fundamental physics and potentially unravel some of the more orderly narratives of cosmic evolution. The confusion they generated was immense, posing questions that seemed, at the time, almost unanswerable within existing frameworks. Imagine the intellectual bravery, or perhaps the sheer stubbornness, required to accept a universe that defies our deepest expectations. For decades, many hoped they simply weren't real. What compelled this profound intellectual resistance, and how did humanity, in its quest for truth, finally overcome it? Yet here we stand in the present era, armed with an overwhelming and continually accumulating body of evidence, both direct and indirect, that unequivocally demonstrates the physical existence of black holes. They are not mere theoretical fantasies, but very real, albeit profoundly strange, components of our cosmos. And precisely because we now know, with certainty, that they do exist, we are compelled, by the very spirit of scientific inquiry, to confront the challenges they pose, to unravel their mysteries, and to glean whatever profound insights they might offer into the universe's deepest, most intricate workings. This resolute acceptance of their reality has irrevocably transformed them from a speculative curiosity into a critical, vibrant frontier of scientific research, demanding entirely new modes of thought and relentlessly pushing the conceptual boundaries of our theoretical frameworks. The journey to understand them is far from over. Indeed, it has only just begun to reveal its deepest layers, hinting at profound truths yet to be unearthed. Black holes are immensely interesting, captivating not merely as exotic astronomical curiosities or distant gravitational anomalies, but as crucial, perhaps even indispensable, theoretical laboratories. Their profound significance becomes particularly evident when we trace back to the groundbreaking work initiated by Stephen Hawking in the transformative decade of the 1970s. His monumental insights into these cosmic entities illuminated a fundamental, inescapable truth: black holes, by their very nature, unequivocally demand that we abandon the intellectual comfort of considering quantum theory and general relativity as separate, independent pillars of physics, operating in isolation within their distinct domains. Instead, they insist, with an almost cosmic imperative, that we think about these two monumental theories together, in concert, as if they were intrinsically intertwined, two halves of a single, more complete, and ultimately more truthful description of reality. This profound recognition places them at the very heart of one of the greatest scientific quests of our age, the pursuit of a unified theory of everything. This quest, this relentless drive to unify these two great intellectual edifices, these dominant paradigms that have so profoundly shaped 20th and 21st century physics into what is often, and quite aptly, referred to as a quantum theory of gravity, represents, in a very real and palpable sense, the Holy Grail for theoretical physicists. It is the ultimate intellectual prize, the elusive pinnacle that promises to unlock a truly fundamental, all-encompassing understanding of the universe, extending from the most minuscule scales of quantum foam to the grandest architectures of galactic superclusters. The pursuit of quantum gravity is an endeavor to reconcile the seemingly contradictory descriptions of reality offered by general relativity, which elegantly describes gravity and the large-scale structure of space-time, and quantum mechanics, which exquisitely governs the behavior of matter and energy at the subatomic level. One speaks of a smooth, continuous spacetime, the other of discrete, probabilistic quanta. For many decades, the persistent and vexing problem for researchers engaged in this quest was a profoundly practical one, where, in the entirety of the natural world, could we possibly find a tangible, observable phenomenon, a real-world crucible, that so unequivocally demands the merging of these two distinct theories? Where, in this vast universe, do the rules of the infinitesimally small collide with the dictates of the immensely large, demanding a single, coherent narrative? Where could a natural laboratory exist where the effects of immense gravity, the very domain of general relativity, manifesting as space-time curvature and the bizarre, probabilistic, and often counterintuitive behavior of matter and energy at subatomic scales, the realm of quantum mechanics, with its intrinsic uncertainty and its ephemeral virtual particles, simultaneously become so pronounced, so inextricably intertwined, that their interaction cannot be ignored, that their separate descriptions simply become inadequate. For a long time, such a place seemed to exist only in the most abstract mathematical thought experiments, perhaps confined only to the extreme and utterly inaccessible conditions of the very early universe, a fleeting epoch, difficult, if not impossible, to probe directly with any empirical means. However, black holes, as our understanding has deepened and our instruments have grown more sensitive, offer precisely this unique and compelling intersection. They stand as the singular, most profound places in nature, as far as we can currently discern, where we encounter an object, a readily inferred, and now directly observed, presence sitting majestically, or perhaps terrifyingly, in the vast expanse of the cosmos. This presence, by its very existence and its observed properties, inexorably demands that we consider both general relativity and quantum theory operating in unison, in a profound and inseparable dialogue. It is within the unimaginably extreme environments surrounding and, we presume, within black holes that these two hitherto separate and seemingly incommensurate descriptions of reality are forced into direct, undeniable, and often paradoxical conversation. This forced reconciliation offers the tantalizing hope that by diligently studying their intricate properties, by meticulously analyzing their baffling behaviors, and by bravely confronting the deep conceptual challenges they present, we might finally unveil a deeper, more comprehensive, and truly unified theory. Such a theory would seamlessly bridge the chasm between the macroscopic world of planets and galaxies and the microscopic realm of quanta, providing a coherent narrative for the universe's operation. It is this fundamental interplay, this inherent conflict and cooperation between general relativity and quantum mechanics at the very boundaries of a black hole, that elevates them to such profoundly important objects of study, not just for the specialized field of astrophysics, but for the very foundations of physics itself, beckoning us toward a grander synthesis of knowledge, a tapestry woven with threads of the very large and the very small. The underlying intellectual ancestry of the concept that would eventually evolve into our sophisticated modern understanding of black holes stretches back an astonishingly long way, reaching much further into history than Einstein's revolutionary theories of the early 20th century. In fact, the genesis of this idea can be traced back to the late 1780s and early 1790s, a fascinating period in intellectual history when the boundaries between scientific disciplines were far more fluid, and what we now call science was often encompassed within the broader realm of natural philosophy. During this remarkable era, two brilliant and visionary individuals, working completely independently of each other and apparently unaware of the other's profound investigations, arrived at essentially the same groundbreaking concept. How could minds, centuries ago, without the full tapestry of modern physics, intuit such a profound cosmic truth? These were John Michell, an English clergyman, a polymath whose intellectual contributions spanned geology, astronomy, and physics, and Pierre-Simon Laplace, the towering figure of French mathematics and celestial mechanics, whose work laid foundations across numerous scientific fields. Both of these extraordinary thinkers approached the problem through the foundational lens of a crucial physical principle, the concept known as escape velocity. Let us pause for a moment to truly and deeply appreciate the concept of escape velocity, as it forms the fundamental cornerstone of this early, prescient understanding of what we now call black holes. Escape velocity, in its most precise definition, is the absolute minimum speed an object must attain to completely and irrevocably break free from the gravitational pull of a massive body, such as a planet or a star, and venture indefinitely into the vastness of space without ever being drawn back by that body's gravitational embrace. To fully illustrate this concept, let us consider our own planet, Earth, a world whose gravitational influence we experience profoundly every single moment of our lives. From the surface of Earth, the escape velocity required for a spacecraft or any projectile to overcome our planet's formidable gravitational grip is approximately 8 miles per second, which, for those who prefer the metric system, translates to about 11 kilometers per second. This is an absolutely incredible speed, far exceeding anything we typically experience in our daily lives, and it serves to underscore the formidable, though often unnoticed, strength of Earth's gravitational field. Now, let us expand our thought experiment. If we imagine a more massive object, something substantially larger and heavier than Earth, for example, our own Sun, a star of immense scale, 1,000,000 times the volume of Earth, the gravitational pull at its surface would, as intuition suggests, be far more intense, proportionally greater due to its colossal mass. Consequently, the escape velocity from the Sun's surface is dramatically higher, residing somewhere in the region of 400 miles per second. This is a truly blistering speed, almost unfathomable in its sheer magnitude, requiring an immense expenditure of energy to achieve. It eloquently conveys the staggering gravitational forces at play in a star of such colossal mass, forces that shape its very structure and influence everything in its immediate vicinity, holding its fiery plasma in a precarious balance. What Michel and Laplace then pondered, with what I consider to be an astonishing blend of intellectual audacity and visionary foresight, was a truly profound thought experiment. They imagined, in their mind's eyes, pushing this concept of escape velocity to its absolute theoretical limit. They asked, could we conceive of a celestial body that is even bigger, even more massive? Could we envision an entire class of stars ever more massive, ever more compressed, truly gigantic stars, such that their gravitational pull at the surface would become so overwhelmingly immense, so utterly dominant, that the escape velocity required to leave their surface would actually exceed the speed of light? The speed of light, as we now understand it through Einstein's theories, represents the ultimate cosmic speed limit, a fundamental constant that nothing in the universe, no particle, no force, no information, can ever surpass. If an object's escape velocity were to exceed this absolute limit, then, by logical extension, even light itself, the fastest entity known to existence, would be rendered utterly incapable of breaking free from its gravitational clutches. And if light cannot escape, then we, or any observer positioned anywhere in the distant universe, would logically be unable to perceive such an object through conventional means. It would remain, by its very nature, utterly invisible, a dark and silent presence in the cosmos, radiating no light to betray its existence. There exists a truly wonderful and remarkably prescient quote from Laplace's scientific paper, an articulation of this very idea that is astonishing in its profound insight, especially considering its vintage. He wrote, stating with remarkable clarity that the largest objects in the universe may go unseen by reason of their magnitude. This statement, penned in the 1780s or 1790s, nearly a century and a half before the observational confirmation of black holes, is a testament to extraordinary intellectual foresight. Laplace was, with uncanny accuracy, envisioning stars where the gravitational pull was so vastly intense, so incredibly dominant, that not even light could escape its powerful grasp, thereby rendering them utterly invisible to any distant observer. Both he and Michel, in their independent but converging lines of thought, referred to these hypothetical entities as dark stars. Now, it is profoundly important to understand that while their intellectual leap was undeniably brilliant and laid crucial conceptual groundwork, these dark stars, as precisely conceived by Michel and Laplace within the framework of Newtonian physics, do not, in that exact original sense, actually exist in our universe. Their Newtonian model primarily focused on the sheer magnitude of mass, suggesting that an object would need to be unfathomably, perhaps impossibly large to achieve such an extreme escape velocity that even light would be trapped. However, they, perhaps understandably given the scientific limitations of their era, overlooked a crucial, almost paradoxical nuance of the problem. While an increase in mass certainly leads to an increase in escape velocity, there's another equally, if not more, potent mechanism by which one can dramatically increase the gravitational pull at the eye surface of an object, and consequently its escape velocity, by intensely compressing it, by squashing its entire mass into an extraordinarily small volume, thereby achieving an astronomically high density. Consider this, a world like our own, reduced to the size of a child's marble. What terrifying power would such a compressed entity wield? Let us explore this fascinating alternative path to gravitational dominance. Imagine, for a moment, taking our planet Earth, a world we know to be substantial in size and mass, with its diameter of nearly 8,000 miles, and subjecting it to an unimaginable, colossal squeezing force. If you were to squash it down, and then continue to squash it further, and then squash it down again, relentlessly reducing its physical radius, you would, in the process, dramatically increase its density. If you were to sustain this extreme compression until the Earth's entire immense mass was contained within a sphere with a radius of just under a centimeter, a mere fraction of an inch, approximately the size of a small marble, then, at that incredibly tiny, hyperdense surface, the gravitational pull would become so extraordinarily intense, so utterly overwhelming, that light itself would be rendered incapable of escaping its powerful, inescapable grip. And this, fundamentally, describes the core essence of the modern concept of a black hole, not primarily a matter of immense size, but a triumph of extreme density over mere bulk, a region where gravity reigns supreme due to an unimaginable compaction of matter. It is a testament to the idea that the concentration of mass, rather than its spread, is the true arbiter of gravitational power, twisting the very geometry of space and time. It is critically important to recall that Michel's and Laplace's calculations, their ingenious thought experiments, and their remarkably prescient imaginings were firmly rooted in the then dominant paradigm of Newtonian physics. Their work predated by over a century the truly seismic intellectual shift that was about to fundamentally transform our understanding of gravity and the very structure of the cosmos. Fast forward to the pivotal year of 1915, a date indelibly marked in the annals of science, when Albert Einstein, with unparalleled intellectual courage and genius, published his general theory of relativity. This was not merely an incremental refinement of existing ideas, it was a radically different, profoundly superior model of gravity, one that completely reconceptualized gravity, not as an invisible force acting across space, but as an intrinsic manifestation of the curvature of space-time itself. A universe where the very stage upon which cosmic dramas unfold is itself an active participant, bending and warping under the weight of existence. And it turns out, with a remarkable consistency, that black holes, these extreme gravitational entities, once mere speculations, not only find a place but are an inevitable and indeed central prediction of general relativity. Einstein's theory provided a far more sophisticated, accurate, and ultimately deeper framework for describing these enigmatic objects, moving well beyond the approximations and limitations of Newtonian mechanics to offer a profound and consistent description of their fundamental nature. It showed that the universe, in its most extreme corners, behaves according to rules far more intricate than previously conceived. The year 1915 marked a watershed moment in the history of science, as Newton's theory of gravity, which had stood as an unchallenged cornerstone of physics for over 2 centuries, was superseded by a more profound and accurate model, Albert Einstein's general theory of relativity. This new theory didn't just tweak Newton's ideas, It completely revolutionized our understanding of gravity, proposing that it isn't a force pulling objects together, but rather a manifestation of the curvature of space-time itself, caused by the presence of mass and energy. Massive objects, according to this new paradigm, warp the four-dimensional fabric of space-time around them, and other objects simply follow the shortest path through this curved geometry, which we experience and interpret as the force of gravity. Yet, despite this radical shift in conceptual understanding, the core idea, the revolutionary thought that there could exist objects in the universe so incredibly compressed, so unfathomably dense, that their gravitational pull could trap even light, remained not only consistent, but became an even more central and inescapable prediction within Einstein's new, more comprehensive framework. The existence of such light-trapping regions was an inherent consequence of space-time curvature taken to its extreme. The first physicist to truly delve into the mathematical intricacies required to precisely describe such a phenomenon, or at the very least, to derive an exact and rigorous solution to Einstein's complex field equations that explicitly characterized such an object, was a man named Carl Schwarzschild. This remarkable individual, a German physicist and astronomer, accomplished his groundbreaking theoretical work under the most challenging and harrowing circumstances imaginable, while serving on the Russian front during the grim years of World War I. Tragically, he would succumb to an autoimmune disease contracted during his military service, just a few months after submitting his monumental paper, making his profound contribution to theoretical physics even more poignant and a testament to his enduring brilliance. And yet, even in the midst of global conflict, a solitary mind wrestled with the universe's profound geometry. What truths could be born from such an unlikely crucible? What Schwarzschild achieved was nothing short of an intellectual marvel. He provided an exact, elegant, and ultimately indispensable solution to Einstein's notoriously complex equations. These equations are designed to meticulously describe the intricate interplay between matter, energy, and the resultant curvature of space and time. Schwarzschild's solution specifically and precisely describes the distortion of space and time in the regions surrounding a star, or, more accurately, an idealized star, a perfectly spherical, non-spinning ball of matter. It was, in essence, a simplified yet incredibly powerful mathematical model, allowing for a rigorous and precise description of the gravitational field generated by such an object. Schwarzschild presented his findings in a letter to Einstein in December of 1915, and the paper was published in January of 1916, an astonishingly rapid turnaround just a few months after Einstein's general theory of relativity itself was fully published. This speed of discovery underscored Schwarzschild's sheer mathematical prowess and profound insight. However, Schwarzschild's solution elucidated something even more profound than just the space-time geometry around a regular star, though he himself may not have fully grasped its ultimate extreme implications at the time. His elegant equations not only explain the curvature of space-time outside a massive object, but they also described what that space would intrinsically feel or experience like if you were to conceptually remove the star itself. Imagine its matter imploding into an infinitely small point, but leave its gravitational imprint, its profound distortion, in the very fabric of the universe behind. And that, fundamentally, is the theoretical description, the precise mathematical blueprint of what we now understand as a modern, relativistic black hole. It is not an object in space, but rather a profound, self-sustaining distortion of space and time itself, a region so intensely curved that it defines its own inescapable boundary, a point of no return for anything, including light, that ventures too close. This solution, now famously known as the Schwarzschild solution, provided the very first precise mathematical understanding of these cosmic enigmas, laying the absolutely critical groundwork for all subsequent theoretical and observational research into black holes. It was the crucial first step into understanding the geometry of the extreme universe. Now, while Schwarzschild's elegant solution, and when I refer to solution, I mean a precise mathematical description that allows us to conceptually perceive a profound distortion in space and time, A warp, a tear, an undeniable bend in the very fabric of the universe itself, did indeed describe the simplest possible type of black hole that we can accurately model within the framework of general relativity. The wider scientific community, for a considerable period, did not truly grasp or think in such extreme terms at all. The concept was so utterly radical, so far removed from the everyday experiences of gravity and even from established astronomical observation, that it was largely regarded as a mathematical curiosity, a peculiar artifact of Einstein's equations, rather than a description of a genuinely real physical entity that might exist out there in the cosmos. The leap from mathematical possibility to physical reality was a difficult one to make, a challenge to human intuition that often precedes true paradigm shifts. Even into the 1930s, this prevailing skepticism and cautious approach are clearly evident in the scientific discourse of the time. Albert Einstein himself, alongside his colleague Nathan Rosen, engaged in profound explorations of this peculiar space-time geometry. They developed models such as the famous Einstein-Rosen bridge, a theoretical construct that later became popularly known as a wormhole, which were mathematically derived from Schwarzschild's solution. However, their own interpretations of these models frequently led them to conclude that such phenomena were not physically realistic or stable in our universe, or at the very least, they represented highly unstable configurations that would quickly collapse rather than persist as enduring objects. I believe it is a fair and accurate assessment to state that, certainly until the late 1930s, and indeed arguably well into the post-World War II era, extending even to the transformative decade of the 1960s, a significant majority of physicists maintained the strong conviction that such things, black holes as we now understand their robust astrophysical existence, simply would not be found in nature. It is a testament to the conservatism inherent in science, not as a flaw, but as a necessary guard against premature conclusions, demanding rigorous proof before acceptance. Thus, these theoretical constructs were relegated to the category of theoretically interesting, offering intriguing avenues for abstract mathematical exploration within the elegant framework of general relativity, but they were generally dismissed as not practically interesting in terms of observable astrophysical phenomena. The primary and most compelling reason for this widespread skepticism was a fundamental challenging question: how, precisely, could such an extreme object ever actually be created in the universe? It is one thing, the argument went, to possess a beautifully crafted and mathematically consistent model of space and time that describes this peculiar, light-trapping object called a black hole. But it is an entirely different and far more challenging matter to demonstrate that nature itself would actually possess the mechanisms to construct such a thing, to engineer the utterly extreme conditions necessary for its formation and subsequent stability. This formation problem was a significant conceptual hurdle, a towering barrier to acceptance. Throughout the 1930s, this pressing question of black hole formation spurred considerable theoretical investigation. A particularly influential and now widely celebrated paper was authored by Robert Oppenheimer, who would later achieve global recognition as the scientific director of the Manhattan Project, and his talented student Hartland Snyder. Their groundbreaking work, published in 1939 just prior to the outbreak of World War II, rigorously explored a critical astrophysical scenario. Could a real massive star in the universe, a colossal celestial body reaching the ultimate end of its life cycle after exhausting its nuclear fuel, undergo a catastrophic gravitational collapse? And, crucially, could it collapse relentlessly, without any apparent physical limit, to ultimately form this peculiar extreme geometry, this entity that we now definitively call a black hole? Oppenheimer and Snyder, through their meticulous calculations, demonstrated that under certain idealized yet physically plausible assumptions, primarily that the star was massive enough and that no internal pressure could resist the relentless pull of gravity once nuclear fusion ceased, a star could indeed behave in precisely such a way. Its own immense gravity, left unchecked, would overwhelm all other known forces, leading to an unstoppable, runaway inward implosion. However, Despite this monumental theoretical breakthrough, the radical idea of black holes remained largely on the fringes of astrophysical acceptance for several more decades. It wasn't truly until the seminal and transformative work of brilliant minds like Roger Penrose, a mathematical physicist, and Stephen Hawking, a theoretical physicist, along with the contributions of several other key researchers in the intellectually vibrant and revolutionary decade of the 1960s, that the scientific community began to seriously contemplate, indeed to accept as virtually certain, the strong possibility that nature would not only permit, but actively construct these extreme objects. Penrose in particular developed powerful mathematical tools and theorems, notably the singularity theorems, which prove that under very general and physically reasonable conditions, gravitational collapse must inevitably lead to the formation of a singularity. The point of infinite density at the heart of a black hole, an inescapable feature of general relativity in such extreme scenarios. Hawking, building on Penrose's work, further solidified the theoretical case for black hole formation. But the universe, it seems, has little regard for our human notions of absurdity. What profound lessons might we learn when our elegant theories clash with the raw reality of the cosmos? There is a wonderfully illustrative quote that I recall with a certain measure of retrospective fondness attributed to Sir Arthur Eddington. Eddington was a distinguished British astrophysicist and an influential colleague of Albert Einstein, known for his refined intellectual rigor and his deeply ingrained adherence to the scientific traditions of his time. He famously, and with an air of absolute conviction, once remarked, "Nature will prevent such absurdities from existing." His statement perfectly captured the prevailing sentiment of many physicists who, at the time, found the idea of an infinitely dense point in space-time, a region of absolute light entrapment and irreversible commitment, simply too outlandish, too contrary to the perceived harmony, order, and elegant predictability of the universe as they understood it. It was an almost visceral philosophical reaction against what seemed like a theoretical monstrosity, an affront to the expected elegance of cosmic laws. Well, as it turns out, in its boundless capacity for surprise, complexity, and often startling extremity, nature does not in fact prevent such phenomena. The universe, in its raw, unfiltered, and profoundly beautiful reality, evidently has no qualms about creating what we humans, with our limited everyday experiences and initial theoretical frameworks, once perceived as absurdities. We now possess an overwhelming and continually accumulating body of robust observational evidence, gathered through a diverse array of sophisticated astronomical techniques, ranging from the precise tracking of stellar orbits around invisible mass concentrations to the detection of powerful X-ray emissions from superheated gas spiraling into unseen objects, and more recently, the direct detection of gravitational waves, those ripples in the fabric of space-time itself, that unequivocally demonstrates that massive stars do indeed undergo catastrophic gravitational collapse to form black holes. This undeniable reality has compelled theoretical physics to move forward, to adapt, to embrace, and to profoundly integrate these once rejected concepts into the very core of our cosmic understanding, forcing us to expand our mental horizons. So, gradually but inexorably, the scientific consensus regarding black holes underwent a profound shift. People began to accept, first tentatively and then with increasing certainty, that these extraordinary objects should, and indeed do, exist throughout the universe. While it is true that we did not achieve the astonishing feat of directly imaging a black hole's event horizon until the 21st century, a monumental achievement accomplished by the Event Horizon Telescope collaboration in 2019, providing the first direct visual evidence. The accumulation of compelling indirect evidence had become undeniable long before that landmark moment. More and more data continued to mount, strongly pointing to the pervasive presence of supermassive black holes, nestled at the centers of nearly all large galaxies, including our own Milky Way, and the widespread existence of stellar mass black holes, born from the catastrophic demise of individual massive stars. These diverse observations, whether through their immense gravitational influence on surrounding matter and light, or through the detection of the powerful gravitational waves generated by their mergers, provided an overwhelming case for their widespread presence and profound cosmic importance. However, once their existence was widely and definitively accepted, physicists were then confronted with the profound and often disturbing consequences. The new reality posed deeply unsettling questions. What does the existence of these objects truly mean for our understanding of the universe? How does it impact the fundamental laws of physics that we thought we knew so well? If there are these regions where space and time behave in such extraordinarily strange, distorted, and ultimately alien ways, where light itself is irrevocably trapped, and where it would appear that anything and everything, every atom of matter, every photon of light, every piece of information that falls in, is, at the very least, locked away from the observable universe forever, seemingly beyond our reach, our knowledge, and our ability to ever retrieve it. These questions opened up entirely new conceptual problems, forcing a radical reevaluation of our most cherished physical principles, particularly those concerning the conservation of information and the deterministic nature of physical laws. The implications were, and remain, truly staggering. So, what then of the intrepid voyager who crosses that invisible threshold? Does time truly cease, or does it merely continue its relentless march, indifferent to our distant perceptions? To begin to truly grasp these profound conceptual problems, the perplexing, mind-bending challenges that arise from the undeniable existence of black holes, it is immensely helpful to first describe, very briefly, the purely Einsteinian description of a black hole, as derived solely from the elegant framework of the general theory of relativity. Let us imagine, then, a black hole from the perspective of an external observer, someone safely situated far away in the cosmos, experiencing it from a distance, perhaps perceiving it with advanced astronomical instruments. What would this distant observer infer about its structure and its defining characteristics? The most defining and absolutely crucial feature, the ultimate boundary, that surrounds the black hole is known as the event horizon. In a profound conceptual sense, it serves as the ultimate demarcation line, clearly defining the frontier between the external universe, the realm from which we observe and interact, and the mysterious, utterly inaccessible interior of the black hole, a region forever hidden from any direct scrutiny or observation from the outside. The event horizon is, in its most fundamental and simplest description, and here I will use a slightly conceptual or simplified explanation, though it proves quite reasonable and accurate for initial understanding, a conceptual sphere in space. The truly critical characteristic of this sphere is this: if you were to cross this boundary, if you were to venture, perhaps inadvertently, into the interior of this conceptual sphere, then even if you possess the ability to travel at the absolute maximum speed allowed by the laws of physics, the speed of light itself, you would find yourself utterly and irrevocably unable to escape. No amount of thrust, no matter how powerful, no amount of energy, no matter how immense, could propel you back out once you have fallen across that threshold. You would be irrevocably committed to a journey towards the black hole's center, unable to ever return to the external universe. Thus, the event horizon acts as a perfect, inescapable one-way membrane, a point of no return, effectively and absolutely separating the interior of the black hole from the external universe. While this conceptual description provides a solid starting point for conceptualization, we will soon appreciate why it needs further, more nuanced refinement to truly capture the full, mind-bending relativistic subtleties inherent in this cosmic boundary. Yet another description, a truly mind-bending characteristic of the event horizon, one that caused considerable confusion, intellectual debate, and profound consternation throughout the early history of black hole research. Certainly perplexing those who first encountered the initial papers in the 1930s and continuing to challenge many post-war physicists was the deeply counterintuitive idea that, when observed from the outside, from a safe distance in the external universe, the event horizon appears to be a peculiar place in space where time itself grinds to a complete and utter halt. This is not a poetic embellishment, a metaphorical flourish, or a philosophical abstraction. It is a direct, undeniable and mathematically rigorous prediction of Einstein's general theory of relativity when considered from an external observer's perspective. Let's illustrate this with a vivid thought experiment. Imagine, for example, that you are experiencing an intrepid astronaut, perhaps equipped with a powerful telescope, valiantly falling in towards a black hole. From your vantage point, safely outside its overwhelming gravitational influence, you would perceive a most peculiar and unsettling phenomenon. You would sense their time passing progressively more slowly, an effect known as gravitational time dilation. The astronauts' movements would become increasingly sluggish, their frantic hand gestures seemingly stretched out over eons, their onboard clock ticking ever more slowly, agonizingly as they approached the black hole. The slowing of time would intensify, becoming slower and slower and slower until, precisely at the theoretical moment they seemed to reach the event horizon, you would perceive their time as having completely stopped. The astronaut would appear, to your distant external observation, to be utterly frozen in an eternal instant, suspended indefinitely, like a photograph, on the very precipice of the cosmic abyss, never quite crossing it from your perspective. This startling and seemingly paradoxical prediction deeply suggested to many early researchers that a star, undergoing the catastrophic process of gravitational collapse, could never truly form a black hole in a finite amount of time, at least not from the perspective of an external observer. It confused them profoundly, leading to significant intellectual discomfort. They reasoned, if a star's surface is collapsing, and as it approaches the event horizon, time for that surface appears to freeze forever, then does it not, in some meaningful sense, become eternally frozen on the horizon, perpetually suspended, never actually completing its journey across the boundary? This line of reasoning spawned all sorts of initial, early conceptual problems, creating significant roadblocks and contributing to the widespread skepticism regarding the actual physical existence of black holes. For a time, it seemed to present an insurmountable logical barrier, a challenge to the very notion of a dynamic universe. However, these apparent paradoxes, these initially bewildering conceptual challenges, were, in time, ultimately resolved through a deeper understanding of the profound implications of relativity. The key to unlocking their resolution lies in a fundamental, one-sentence insight regarding the very nature of relativity. Time can indeed appear to stop from one specific perspective or frame of reference, but simultaneously it can continue to pass at its usual, normal, unimpeded rate from another distinct perspective. This is the very essence of relativistic physics, the radical notion that measurements of time and space are not absolute, universal constants, but are instead relative, depending intrinsically on the observer's state of motion and gravitational environment. There is no single privileged cosmic clock. Indeed, let us now consider the perspective of the intrepid astronaut themselves actually falling into a black hole. For a sufficiently large black hole, such as the supermassive ones we find majestically residing at the centers of galaxies, which possess gentler tidal forces over greater distances, making the immediate transition less violent, the astronaut would, remarkably, perceive absolutely nothing unusual, no dramatic tearing sensation, no sudden jolt as they smoothly, seamlessly, and quite unremarkably cross the event horizon into the black hole's interior. Their own watch, strapped to their wrist, would continue to tick at precisely 1 second per second. Their experience of time would be entirely normal, at least for a while. The only immediate indication of having crossed the point of no return might be an increasing difficulty in communicating with the outside universe, as their radio signals would struggle against the overwhelming gravitational pull, becoming increasingly redshifted and eventually falling silent, forever trapped within the black hole's influence. So, while time appears to freeze on the horizon from an external, distant perspective, for the intrepid explorer making the journey, time passes as usual, ticking away at its normal rhythm. The true horror or wonder lies in the fact that there is no turning back, no path to escape once that invisible line is crossed, for the future lies solely inward. Black holes are thus replete with these kinds of apparent conceptual challenges, these mind-bending relativistic effects, which, upon closer inspection and a deeper, more comprehensive understanding of Einstein's general theory of relativity, turn out not to be fundamental inconsistencies or contradictions at all. Instead, they are revealed as intrinsic, central, and indeed necessary parts of Einstein's magnificent theory, powerfully illustrating the theory's counterintuitive yet mathematically consistent and empirically robust nature. This initial confusion, therefore, which had plagued early researchers, was eventually dealt with and ultimately resolved. By the 1960s, the physics community had largely developed a robust, coherent understanding of what these enigmatic objects truly are and how general relativity exquisitely models them, at least from a purely classical gravitational standpoint. The event horizon, once a source of paradox, became a testament to the theory's profound predictive power, a beacon pointing to a deeper truth. Nevertheless, despite the resolution of the event horizon paradox, there remains a central, profound, and indeed deeply unsettling problem, one that is still very much unsolved and continues to represent one of the absolute frontiers of theoretical physics. This is the vexing question of what truly lies at the very heart, or rather, at the theoretical core of a black hole. I must choose my language here with utmost care and precision, as the conventional notions of center, or place, or even location begin to fundamentally break down and lose their usual meaning in such unimaginably extreme environments. If the event horizon is a boundary of no return, then what lies beyond, at the very heart of this cosmic abyss, where space and time themselves abandon their familiar roles? In the pure, unadulterated, and classical framework of Einstein's general theory of relativity, it is, strictly speaking, not entirely accurate or conceptually correct to talk about a center of a black hole in the way we might conventionally imagine the geographical center of a planet or the stellar core of a living star. What we are conceptually perceiving, what the mathematics points to, is something called a singularity. Our everyday intuition, constrained by our experience of finite densities and finite spaces, might naturally lead us to think of it as an infinitely dense point, an infinitesimally tiny, immeasurably small region of spacetime into which the entirety of the massive star that collapsed to form the black hole has been utterly crushed. This is certainly a natural, albeit simplified and ultimately incomplete, way for the human mind to grasp such an extraordinarily extreme concept. It provides a visual anchor, even if inaccurate, in the boundless ocean of the unknown. However, when one delves more deeply and precisely into the sophisticated mathematical descriptions within pure general relativity, particularly when meticulously studying the elegant and powerful maps of space-time curvature, such as the celebrated Penrose diagrams, named after the brilliant mathematical physicist Roger Penrose, who pioneered their use, a far more astonishing and mind-bending reality emerges. These diagrams, these abstract cartographies of space-time, reveal that the singularity is not, in fact, truly a place in space at all. It is not a fixed, static geographical location that one might eventually reach by simply traveling inward through the black hole's interior. Rather, the singularity is revealed to be a moment in time. More profoundly and unsettlingly still, for anything and anyone that falls into the black hole and crosses its event horizon, this singularity represents not merely a future point, but the absolute inevitable end of time itself. There is no escape and no future beyond this point, for time itself runs out. So, one particularly evocative and accurate way of perceiving what has fundamentally happened when a star undergoes catastrophic gravitational collapse to form a black hole is to understand that space and time, those two fundamental components of our reality, become so extraordinarily distorted, so warped, twisted, and profoundly curved that their usual roles, their conventional meanings and properties, in a profound and almost poetic sense, actually swap. And so, what we initially thought of as an infinitely dense point, a specific place in space, the ultimate center at the heart of the star's collapse, if you like, a destination within a physical dimension, actually transforms into an inescapable future moment in time. And indeed, the absolute end of time for anything caught within its grasp, that ultimate boundary that we call the singularity. But here lies the enduring mystery. the precise physical nature of that thing, that singularity, that ultimate end of time, that region where space-time itself breaks down, was not and remains to this very day not fully understood by our current physical theories. It stands as one of the greatest, most intractable, and most profound mysteries in all of physics, a stark reminder of the limits of our current knowledge. For many, many years, it has been widely accepted, almost as an article of faith within the theoretical physics community, that to truly explain, comprehend, and perhaps even smooth out the singularity, we will fundamentally require what is termed a quantum theory of gravity. This is a deeper, more encompassing, and more coherent theory of gravity, one that can seamlessly reconcile the macroscopic realm of gravity, as described with such elegance by general relativity, with the microscopic, probabilistic, and often bizarre world of quantum mechanics. The singularity is where these two theories, in their current formulations, clash violently, pointing to the need for a unified understanding, a grand theory that sees the universe as a seamless whole. For many, many years, indeed until quite recently in the grand, sweeping arc of scientific progress, the prevailing sentiment among many leading physicists was a sense of resignation, a thought pattern that went something like this: well, there we are. We acknowledge that we have a profound and deeply unsettling problem with the singularity, but, in truth, we don't really have any direct physical access to it, as it is irrevocably locked away behind the impenetrable veil of the event horizon. Furthermore, we currently lack the necessary conceptual tools, the appropriate mathematical frameworks, and certainly the observational means to directly explore it or probe its ultimate nature. So it may well remain an inscrutable mystery, a frustratingly inaccessible enigma for a century or more to come. It's simply not clear what concrete steps we can take to address this fundamental theoretical breakdown. The problem of the singularity, while acknowledged as a critical flaw in general relativity's completeness, seemed for a long time an insurmountable theoretical dead end, often set aside in favor of more tractable and immediate scientific questions. However, a truly profound and revolutionary shift in black hole research, a paradigm-altering realization, began to unfold, spearheaded by the brilliant and indefatigable work of Stephen Hawking in the mid-1970s. The essence of this revolution, this pivotal insight, was the astonishing recognition that, contrary to previous assumptions and prevailing wisdom, there were in fact deep and fundamental conceptual problems arising not just in this extreme, utterly inaccessible, and highly speculative region at the singularity, whatever that enigmatic thing might ultimately be, but, crucially, at the event horizon itself. But what if the deepest secret lay not in the unapproachable core, but at the very edge, the shimmering boundary where our most cherished theories begin to fray? This was a truly paradigm-shifting and utterly unexpected insight, an extremely interesting and profoundly challenging development for the entire field of theoretical physics. Why was it so significant? Because at the event horizon, unlike the singularity, we possess a strong and well-justified expectation that the laws of nature as we currently understand them, the laws for which we possess full mathematical and conceptual control, the laws of both general relativity and quantum mechanics, applied in their respective domains of validity, should perfectly apply. The event horizon is not, in a fundamental sense, a region of infinite curvature or infinite density. It is, locally speaking, a perfectly ordinary place in space-time, albeit one where gravity's effects become dominant and profoundly alter the causal structure of the universe, dictating the flow of information. So, the shocking fact that fundamental conceptual problems were demonstrably emerging precisely at this seemingly ordinary yet crucial boundary meant that we were faced with an undeniable conflict, a deep and troubling clash of principles between our two most successful and fundamental theories of nature: general relativity, the theory of the very large, of stars and galaxies and quantum mechanics, the theory of the very small, of atoms and subatomic particles. This was not a subtle disagreement, but a cosmic shouting match. And that, ultimately, is the profound reason why the event horizon of a black hole, and indeed black holes themselves, have ascended to such a pinnacle of fascination and importance in modern physics. It is precisely because they provide a concrete, albeit extreme, astrophysical setting, a cosmic crucible, where we firmly believe, and indeed we are correct in that assumption, it seems, that we possess full intellectual and physical control of the underlying physics, at least when considering general relativity and quantum mechanics in isolation. Yet, when we attempt to apply both theories simultaneously to bring them to bear on the subtle and extreme phenomena occurring at this critical boundary, a fundamental inconsistency, a deep clash of principle, unmistakably arises. This makes black holes invaluable laboratories, cosmic thought experiments brought to life, where the very limits of our current understanding are tested, providing the tantalizing promise of revealing a deeper, more comprehensive, and truly unified theory that resolves this foundational conflict. It is a cosmic tug-of-war, demanding a synthesis of our greatest physical ideas, a new melody for the universe's grand symphony. The modern revolution in our thought, a profound shift in perspective that is still very much ongoing within the scientific community, particularly in our understanding of black holes and the elusive quest for quantum gravity, truly does begin with the groundbreaking and audacious work that Stephen Hawking undertook in the mid-1970s. It was during this period that Hawking, through his meticulous and brilliant calculations, arrived at a conclusion so startling, so counterintuitive, that it fundamentally reshaped our entire conception of these cosmic behemoths. In his own wonderfully concise and evocative words, Stephen Hawking definitively showed that black holes ain't so black. This seemingly simple phrase, almost colloquial in its phrasing, encapsulates a revolution in scientific thought, a paradigm shift of immense proportions, revealing a universe even stranger and more marvelous than we had dared to imagine. Prior to Hawking's work, we had consistently described black holes as absolute, inescapable prisons, in a very literal and unambiguous sense. We pictured them as an utterly impenetrable region of space, a cosmic void from which nothing, not even the most fleeting particle of light, could ever hope to emerge once it had crossed the event horizon. They were considered ultimate absorbers, perfect gravitational traps, cosmic dead ends where matter and energy simply vanished from the observable universe forever. Their interiors were thought to be forever sealed off from communication or interaction with the outside world, silent, dark, and eternally unchanging. However, what Stephen Hawking, through a landmark series of papers and what can only be described as a monumental tour de force of theoretical calculation and conceptual insight, definitively demonstrated was something utterly astonishing, something that completely upended this prevailing view. He showed that if you meticulously consider the principles of quantum theory, or quantum mechanics, operating in the immediate vicinity of the event horizon of a black hole, then a completely different, unexpected picture emerges. You discover, against all classical intuition, that these objects do not remain perfectly black, perfectly silent, or perfectly isolated. Instead, they glow. They actively produce and emit a continuous stream of particles into the surrounding universe. They possess a discernible temperature, a property usually associated with radiating bodies, not purely geometrical distortions of space-time. This entity that we had previously envisioned solely within Einstein's general theory as pure geometry, as simply a profoundly distorted and static region of space and time, actually emits particles, radiates energy, and thereby interacts dynamically with the wider cosmos. This astonishing emission is now famously known throughout the scientific world as Hawking radiation. Could it be that these cosmic devourers, these ultimate traps, are not merely destroyers, but subtle, slow emitters whispering information back into the universe? Hawking himself, in his pivotal 1974 paper, which introduced this revolutionary concept, offered a hand-wavy description, an intuitive and accessible picture to help grasp the complex underlying quantum phenomenon. He openly acknowledged that a full and precise understanding truly requires the rigorous mathematical formalism of quantum field theory in curved space-time. Yet, This conceptual model, this illustrative analogy he provided, is incredibly useful and continues to be a powerful tool for conceptualization. The core idea, the central imaginative leap, is to envision zooming in, with an almost impossible level of magnification and a metaphorically slowed sense of time, on any seemingly empty piece of space, even the space directly in front of you at this very moment. If you could, through this conceptual microscope, zoom in to truly microscopic subatomic scales and metaphorically slow time down to an infinite crawl, what you would perceive is not, in fact, emptiness at all. Instead, you would experience a ceaseless, frenetic, and ephemeral dance of particles constantly flickering in and out of existence. These are often referred to as virtual particles, appearing momentarily in entangled pairs, a particle and its corresponding antiparticle. They spontaneously materialize from the quantum vacuum, a concept that fundamentally redefines empty space as a bustling, energetic realm, a frothing, seething sea of ephemeral quantum activity. These virtual pairs exist for an infinitesimally brief moment, a fleeting fraction of a second allowed by the Heisenberg uncertainty principle, which states that one cannot simultaneously know with perfect precision certain pairs of properties such as energy and time. This quantum jittering, this borrowing of energy from the vacuum, is quickly repaid, and then, just as quickly, they annihilate each other, returning their borrowed energy to the quantum vacuum from which they momentarily sprang. This phenomenon is a fundamental and experimentally verified aspect of quantum field theory. It dictates that the vacuum of space is not a quiescent, inert void, but rather a bubbling, frothing, seething sea of ephemeral quantum activity, a constant creation and annihilation of virtual entities, even in the deepest void. Now, extend this profound understanding of the quantum vacuum to the unimaginably extreme environment found immediately around the event horizon of a black hole. This same incessant process of virtual particle-antiparticle pairs spontaneously appearing and disappearing is happening everywhere, including, critically, right near that elusive and crucial boundary. The immense gravitational curvature and the unique properties of spacetime at the event horizon introduce a critical asymmetry, a decisive breaking of the usual symmetry of these virtual pairs. It can happen, with a certain probability, that one of these virtual particles, say the particle in a particle-antiparticle pair, momentarily materializes on the inside of the event horizon, while its entangled partner, the antiparticle, simultaneously appears on the outside edge. In this extraordinary and gravitationally distorted scenario, the particle that finds itself on the inside of the event horizon is irrevocably drawn into the black hole's interior, its fate sealed, unable to ever escape its powerful gravitational embrace. Its partner, however, the one that materialized on the outside instead of performing its usual quantum dance of annihilating with its twin, now finds itself alone, at the very edge of the black hole's immense gravitational well. The extreme tidal forces and the intense energy conditions near the horizon can provide the necessary energy to transform this virtual particle into a real, observable particle, allowing it to escape into the wider universe, to travel freely away from the black hole's grip. It has, in essence, been made physically manifest and real by the proximity and the extreme gravitational field of the black hole. The other partner, meanwhile, remains trapped forever within the black hole's interior, destined for the singularity. As this newly realized particle heads off into the universe, it carries away a tiny but measurable amount of energy. This energy, by the fundamental laws of physics, particularly the conservation of mass energy, must ultimately be sourced from the black hole itself, specifically from its total mass energy content. This continuous rain, or glow, of particles escaping from the event horizon, this steady outflow of energy and matter, is what constitutes Hawking radiation. And the implications of this phenomenon, as we shall explore, are nothing short of profoundly revolutionary, challenging some of our most deeply held beliefs about the universe, whispering new possibilities into the cosmic silence. So, while that conceptual description offers a simplified, intuitive picture of what's happening at the quantum edge of a black hole, the profound upshot of Hawking's discovery is truly revolutionary. Imagine this entity, this black hole, which we once conceived of as an eternal, immutable, and utterly dark prison. Now, we understand it is glowing. It is not merely a static, unchangeable space-time geometry. It is actively emitting particles, constantly bleeding off energy into the surrounding universe. If an object, any object, continuously loses energy, then by the fundamental and unforgiving laws of physics, it must inexorably be shrinking. And if it is shrinking, then, given enough cosmic time, it will eventually evaporate completely, meaning that one day it will simply be gone. This profound realization overturns a previously held dogma. Black holes are not, in fact, eternal prisons. They possess a finite lifetime, a cosmic expiration date determined by their mass. The smaller the black hole, the higher its temperature and the faster it evaporates. Conversely, colossal black holes, like the supermassive ones at galactic centers, which can be millions or even billions of times the mass of our Sun, would take unimaginably vast stretches of time, far exceeding the current age of the universe, which stands at some 13.8 billion years, to fully evaporate. But the principle holds, eventually, after eons of radiating away, the entire black hole will have dissipated, disappearing completely from existence. This implies that whatever initially fell into the black hole throughout its immense history, every star, every planet, every particle, every quantum of information is, in some form, ultimately returned to the universe, albeit through this peculiar and gradual process of Hawking radiation rather than in its original coherent state. This leads directly to the question, the central, most vexing, and deeply challenging question that was immediately raised by Hawking's revolutionary calculations, a question that has haunted theoretical physicists for decades. What precisely happened to all the stuff, all the matter, energy, and critically, information that fell into the black hole over its immense lifetime? According to the way we have described it thus far, based purely on Einstein's classical general theory of relativity, all that stuff somehow inexorably journeys to the singularity. This singularity, as we discussed, is that enigmatic thing, that end of time, a region of space-time so unimaginably convoluted and distorted that our current physical theories completely break down, we simply don't understand how to describe it at all. But then, as Hawking's work revealed, one day, the entire black hole is utterly gone, having evaporated away. All that is left in the far, far future is this diffuse Hawking radiation, those energetic particles that were meticulously produced in the vicinity of the event horizon over countless eons. The crucial inquiry, therefore, becomes this: is it possible, even in principle, if you possess the inconceivable technological prowess and theoretical understanding required to collect all of that Hawking radiation, every single emitted particle, every quantum of energy, throughout the black hole's entire immense lifetime, that the information about everything that ever fell into the black hole throughout its history would somehow be imprinted, meticulously encoded, within that outgoing radiation in the distant future? Is this true, a fundamental truth of the universe, or is it not true, implying a radical, irreversible loss of information? You might pause at this point and consider, why is this question so profoundly important? It seems like a rather esoteric, almost random question in the grand scheme of cosmic inquiry. The answer lies at the very heart of quantum mechanics, one of the two foundational pillars of modern physics, and specifically concerns one of its most deeply cherished and empirically robust principles, the conservation of information. To truly underscore its immense significance, let's consider a simpler, more relatable analogy from our everyday world, but extended to its quantum mechanical extreme. Imagine for a moment that I take any ordinary object present in this room, a book, a table, a piece of sophisticated equipment, perhaps a memory device, anything at all that contains a specific arrangement of matter and, by extension, information. Now I decide to destroy it utterly. I could set it ablaze, incinerating it completely to ash and smoke. I could crush it in a powerful hydraulic press, reducing it to dust. I could even place it at the epicenter of a nuclear detonation, utterly atomizing it into a chaotic plasma of fundamental particles and pure energy. The goal, in this extreme thought experiment, is to completely, thoroughly obliterate its macroscopic form, seemingly erasing its existence. In the realm of fundamental physics, specifically within the robust and extensively tested framework of quantum mechanics, a deeply cherished and empirically validated principle states that information is conserved in the universe, as far as we know. This is not a mere hypothesis, it is a bedrock principle that underpins our understanding of how physical systems evolve. It means that if you could, in theory, collect every single piece of that thing that I detonated or incinerated, every quantum of radiation emitted, every photon of light, every radio wave, every X-ray, every fundamental particle, every electron, every quark, every neutrino, every subtle tremor in the surrounding environment, every minute detail of its disintegration. Then, in principle, if you were clever enough, if you possessed an impossibly advanced computational capacity, an omniscient understanding of the underlying physics, and the ability to reverse every quantum interaction, you could theoretically reconstruct the original object that I had destroyed, atom by atom. The information describing its exact quantum state, its precise arrangement of particles, its unique properties, is never truly lost. It merely transforms from one form to another, encoded in the emergent radiation and particles. Every known law of nature, every experiment ever conducted, every piece of evidence from particle accelerators to cosmological observations reinforces this profound principle that information is conserved. It is a fundamental tenet upon which much of our understanding of the universe's predictable, deterministic evolution rests. It is a statement that the universe, at its deepest level, does not have an undo button in the way that implies complete erasure. Rather, it merely shuffles its deck of quantum cards, preserving the cosmic ledger. The profound problem, the monumental paradox that emerged from Stephen Hawking's initial groundbreaking calculation regarding the process of black hole evaporation through Hawking radiation, was this: his work seemed to suggest, unequivocally, that in this unique cosmic scenario, information is not conserved. His calculations indicated that black holes are, in essence, perfect erasers of information, the universe's only true delete button. To put it very bluntly, and in a way that truly highlights the severity of the intellectual challenge, Hawking's initial calculations stated that once that black hole had completely evaporated away, once it had vanished entirely from existence, then even in principle, there would be absolutely no way, no conceivable method, no amount of computational power, no theoretical ingenuity that could enable you to learn anything, to reconstruct anything at all about the specific nature or properties of the things that had fallen into it throughout its entire history. This includes not only every object that ever plunged across its event horizon, whether a simple atom, a complex organism, or an entire star system, but even the very massive star that initially collapsed to form the black hole itself. The information, it seemed, was simply gone, annihilated from the universe. So, black holes, in this initial theoretical picture, were portrayed as the ultimate cosmic information erasers. They represented the only objects or processes in nature, as we could conceive of them, that seemed to unequivocally violate this fundamental principle of information conservation, a principle so deeply ingrained in our understanding of quantum mechanics. This was not a minor theoretical detail, it was a head-on collision, a fundamental incompatibility between general relativity and quantum mechanics at their most basic, most fundamental levels. This stark contradiction, this deeply unsettling challenge to one of physics' most cherished and robust tenets, became famously known throughout the scientific world as the black hole information paradox. It didn't just pose a puzzle, it presented a profound crisis for theoretical physics, an apparent dilemma where one of our most successful and beautiful theories, general relativity, predicting black holes, seemed to fundamentally contradict another equally successful and fundamental theory, quantum mechanics, upholding information conservation. The resolution of this paradox, The attempt to reconcile these two titans of modern physics in the context of black holes has driven much of the most advanced and speculative research into quantum gravity for the past 5 decades, propelling physicists towards new, often revolutionary, and sometimes truly bizarre ideas about the very nature of space-time, the essence of information, and the ultimate fabric of reality itself. This paradox, therefore, is not merely a theoretical puzzle or an academic debate. It is a profound doorway to a deeper, more unified understanding of reality, guiding our exploration into the unknown frontiers of physics, inviting us to contemplate the universe's most intricate and perplexing secrets, lulling us into a state of deep reflection and quiet wonder as the cosmos continues to unfold its mysteries, one captivating enigma at a time. The answers, though elusive, promise to be as beautiful and profound as the questions themselves, revealing the astonishing ingenuity of nature.